All right, I think we can start. Good afternoon, everyone. It's my pleasure to introduce our guest speaker, Dr. Ahmad Al Rashdan. He is a research scientist, and development scientist at INL, currently in the Nuclear Science Division.
GSAC asked to make an announcement at
Sure.
the beginning, and I need to make sure that this is working. Is this working okay for the guys? And it's on a distance? Can you give me like a thumbs up?
Yeah.
Good job, thank you.
All right, are we good to go?
GSAC said they wanted to make an announcement.
Would you like to?
We have two events this week. The first one is happening today after the Tucson elections. There's the final happy hour before the semester ends. The second event is December 2nd. It's the town hall meeting for the full semester. It's from 1 to 2 and 101 hours. Looking forward to seeing you all. Thank you.
No pizza?
Yeah.
Okay.
Sorry, thank you.
It's okay. All right. So Dr. Al Rashdan, he's a research and development scientist at INL. His area of expertise is automation and instrumentation and control. He has been in this field for more than 15 years. He worked at INL, he worked at Texas A&M, at IAEA, and Germany. His education also is multinational. His Ph.D. from Texas A&M in nuclear engineering, master in information technology and automation systems from Germany, and undergraduate from Jordan University. We're very pleased to have him here. I'll let him start the presentation.
Thank
There
you.
is one here. Do you want to stay in flipper sides?
No, I'll just manage them without the little points. That's fine.
Okay, sorry, I didn't know there were.
Do I need a microphone or anything? Do I need to wear this?
They can hear you, and there's a microphone in the
perfect.
camera.
Great. Hi. Thanks again for the introduction. Really glad to be here today. As was mentioned earlier, I'm a senior R&D scientist at Idaho National Laboratory. Not sure how many of you have heard about INL before, but we are the nuclear lab, the Nuclear National Lab. Conduct a lot of research that relates to nuclear energy and enabling nuclear energy for the nation. I will be moving around a lot, so I hope you won't be distracted. And at some point I might even run, but don't get distracted with that. The topic of my discussion today is automated anomalies detection and analysis for remote monitoring. Wrong one. Let's try this one. There you go. All right. So this is not going to be all about the anomaly detection topic, and I'm going to explain to you what anomaly detection is in a minute. So I wanted to give you some insight about the program that is funding a lot of this work that I'm presenting today. This work is first of all conducted by INL, Idaho National Lab, which is where I work. I've been with them now for almost 8 years. Most of my work is for the Light Water Reactor Sustainability Program. And this is a DOE program that was started, I think it's late 2000s. It was at that time, the US government was worried about the future of nuclear energy in the nation because of the fact oil and gas prices were very low. Nuclear as an industry, nuclear power as an industry is expensive. So we wanted, or the US government wanted to figure out a way to assist nuclear power plants to become more sustainable. So they launched this program into why is nuclear expensive? How can we help them become more sustainable? And of course, there's a national an energy security aspect into this, that we want nuclear to be part of our energy grid, and that's why this whole program was started initially. And then going through the various stages of program development, it has evolved into multiple pathways. So I'm going to give you an introduction to those pathways and specifically talk about plant modernization pathway, which is the one where most of my work has been focused. And then from there, I'm going to talk about anomaly detection. So anomaly detection, in case you don't know what that is when we're trying to find subtle issues in the plant that could escalate into something catastrophic and cause an outage, or something else in the plant that needs operators' attention. And in order to do that, we've looked into multiple data-driven methods, and I'm showing here some examples of those methods. So unsupervised machine learning approaches, and if you're not familiar with unsupervised machine learning, it means that you're trying to teach a machine to replicate the decision-making process of a human without providing it with any form of prior knowledge. So usually if you talk about supervised machine learning, you are adding labels to some data set, and you're informing the machine that in the past, when you saw this pattern, this was the decision made. With unsupervised, you don't have those labels. So you're asking the machine to determine on its own if there's something abnormal going on. Now with the semi-supervised, we went in our research from fully with no labels to maybe some labels. And I'll explain to you why we ended up with this situation. And then once we did the anomaly detection side of things, we went one step ahead and we said, okay, so now we know that you have an anomaly. When you have that in the plant, you have people dedicated to look at those anomalies and understand why they happened, what is the root cause for those anomalies, and how can we overcome them. And that's the unsupervised root cause analysis. And there's a reason why I say here unsupervised, unsupervised, and semi-supervised. Most of the work I'm showing you today is model independent. We don't have models. We don't build models for equipment or for things we're monitoring. And we just run a data-driven approach into trying to identify if there is an issue and what is the cause of the issue. And then I'm showing you the last bullet, which is crossed. And the reason I crossed this is it's something also dear to me, and we've been working on this, especially recently, but I just don't think I will have enough time to talk about it, but I just still wanted to mention it. And this is transient condition scalability. So when we do anomaly detection, so if I have a lot of data that represent a certain regime in the plant, let's say your plant is running at 100% power all the time, or most of the time. And then you have that 1% of the time where it's running at lower power because something happened in the plant, they have to reduce the power rating and operate at lower levels. Currently, when we do machine learning, and we have taught the machine learning model to understand how the plant operated for a past decade or two on 100% power, when it goes down to 80% power, that's by default an anomaly. And what we're doing here is we're trying to scale the models we create from the 100% power to work at lower powers. But as I mentioned earlier, I'm not going to be talking about this today because it's a whole topic of research that I can spend hours on. And then at the end, I'm just going to give you some examples of other efforts we're doing. So going out of anomaly detection, just give you some broad idea of some of the efforts we have been working on. All right. So as I mentioned, this is the program, the Life Water Reactor Sustainability Program mission. And if you're not familiar with the figure to the left, that is how our a typical US nuclear power plant would look like. Very analog. It goes back to the 70s, 80s, and very human demanding. And this is to the right. You have a modern airplane with their very autonomous way of operation. You can switch the airplane to autopilot and it will run on its own. Now, why do we care about this? So I mentioned to you earlier that nuclear is our was, and maybe it's kind of still in there, but it's getting much better now, was suffering economically when compared to fossil industry. And to give you perspective, in a nuclear power plant, let's say we have two power plants. One is in nuclear and one is fossil. And both of them are generating the same power. So let's say they're generating 1,000 megawatt electric, or 1 gigawatt electric. In a typical nuclear power plant, you would have almost 10 times the amount of labor that you would have in a fossil plant. So if in a fossil plant you have 50 staff in total working on the plant, you probably would end up around 500 or so in a nuclear power plant. And keep in mind, it's not only the manpower, those the people working in a nuclear power plant have to have a very special set of skills and qualifications, so they are more extensive than the ones you have in a fossil plant. So most of our industry costs is associated with our workforce costs. In the fossil plant, most of your costs are associated with the fuel. Nuclear fuel compared to fossil fuel is very cheap. So we're trying to solve this problem, which is how can we reduce the manpower in nuclear power plants? How can we help them become more sustainable without compromising the safety? Most of those added workforce in the nuclear industry were driven by safety concerns. So in the past, the industry resorted to adding more people when they have doubts about things. And that's why we ended up where we are now. Because when the industry started, that wasn't the case. All right, so the program has 5 different pathways, and every pathway has its own objective. So we have the plant modernization pathway, which is the pathway I spend most of my time on. And the aim here is to look at how can we digitize the plant, how can we modernize the plant, and what kind of technologies can we introduce to enable more efficiencies. So that's the kind of the automation side of the program. And then we have the flexible plant operation and generation. And in this case, we're looking at, or this pathway, we're looking at, okay, so if electricity is really expensive when using nuclear compared to fossil, can we use this energy for other processes other than electricity? Because there are some unique features of nuclear that would enable us to do so. And one of the most common applications or uses for this pathway has been energy generation. Hydrogen generation. So hydrogen production, and that has been actually getting a lot of attention nationwide. So we're looking at how to enable nuclear power plants to use some of the heat generated for hydrogen production, because nuclear is clean energy. So you are creating a clean pathway to get to hydrogen versus, for example, using fossil to create hydrogen, which is you're ending up burning fossil energy anyway. So the benefit is gone. Now, the third pathway is risk-informed system analysis. And in this pathway, we create analysis methods and tools. And the focus mainly here is to risk-inform whatever processes or methods we develop and apply in our nuclear power plants. So just like I mentioned to you in the first one, we're creating technologies. This is where we actually introduce the risk element. And that's part of the reason why I'm here today, because I've been discussing projects related to risk informing some of the automation aspects. And then we have materials research. Since our nuclear power plants are 40, 50 years old or so, we do expect that we'll have aging issues with materials, and this pathway is looking into quantifying what kind of issues we have and how can we monitor them, and what kind of mitigation we need to perform to mitigate any potential issues. And then we have physical security. And this is one of the most recent pathways. And the reason we started this is in a nuclear power plant, your security workforce is one of the biggest workforces in the plant. So they have a lot of guards. And if you have been to a nuclear power plant, you would know what I'm talking about. Because no matter where you are in the plant, you will see guards walking around and checking on things. So we wanted to look at technology that can optimize this to help us reduce the workforce requirements. Now, let's go one step deeper into plant modernization pathway, which is the pathway I work on mostly. There are 2 different objectives. In one objective, we're trying to create technologies, solutions, guidelines, reports. So our aim is to enable the industry to innovate and adopt new technologies. So in some cases, we find research gaps and we go and conduct that research to close the gaps. In others, we create demonstrations for the industry to look at the demonstrations and adopt them if they see value in them. And of course, this is all funded by the government, so it reduces the risk on the plant, the financial risk. And then the other objective is looking at the business model. So it's not only about creating solutions and technologies. You also need to figure out how are those technologies going to help the plant. So very often in the past, we used to create solutions, and it became like we have a hammer and we're looking for a nail problem. in reality, you really want the nail to drive what kind of tool you want, or the problem to drive what kind of solution you want. So this is where we drive things by the business case. Well, the left objective is where we innovate and create the solutions to address the business case. And under each of those objectives, we have 4 different research areas. And the one I have to the extreme left is called INC architecture. And the aim of this research area is to figure out or to develop a new framework for instrumentation and control, the infrastructure of the instrumentation and control in nuclear power plants. Because keep in mind, I showed you that picture earlier, and the control rooms are very analog. And now we want to move to something very automated, very advanced. So we have to innovate and figure out how are we going to upgrade those infrastructures and get something more modern to adapt to the modern technologies. And then we have data architecture and analytics. And this is where we create a lot of our monitoring solutions, automated solutions. So wherever you have people doing something in the plant, this is where we do research into creating automation solutions for that. And then we have human and technology integration, which is where we add the human element to the mix. So it's not always about just automating everything. You also need to figure out what is the human role and how do we mix this or mesh this in a more effective way with technology. And finally, on the other objective, we have the integrated operations for nuclear, and that's where the business cases are, our end state business case and model is presented. And we call it integrated operation for nuclear, meaning that everything should be integrated in one bigger picture, or bigger model. All right, so under these different research areas, I know this is not easy. So I took you initially from the program. The program was identifying what the mission is. I took you one step deeper. I showed you all the different pathways, and there were 5 of them. And then I took you one step deeper into one pathway, and we went into 4 different research areas. And then under each research area, you have multiple projects. So you can see we just went into 4 levels of zoom in to get to the project I'm going to be talking about today. There's a lot of effort going on and within this program to help the industry. Now, those different projects I'm showing you here have different objectives, and I'm going to go through them really quickly before I dig into the one in the orange rectangles. So MCR, the first one, is modern control room modernization. So we look at the control rooms, which I just showed you earlier, and how can we change them from where they are now into the digital control rooms, the modern ones. And there are many challenges there, and nothing that we cannot overcome, but there are challenges there. A lot of it relates to human factors, and that's where we do that research. So we design different control rooms. We use technologies like VR and others to evaluate how those control rooms would perform with the operators. We conduct studies and so on. And then we have INC modernization, and this is looking at the infrastructure, as I mentioned to you earlier. So in order to have modern control rooms, you need to have a modern infrastructure. Otherwise, those control rooms would not be able to acquire and use that information that is present in the plant. So that's where this project comes in. And then we have 3 different projects in the middle. One is called condition-based monitoring, focused mostly on maintenance activities in the plant. What do maintenance plant do? They inspect things. They make sure everything is running fine. They do surveillances. There are many things they can do. And this project is basically focused on those. The project I'm going to talk about today is advanced remote monitoring for operations readiness. So that's the focus on the other organization, which is operations. What do operators do? Well, in summary, they do two things. One is they collect information and data. And second, they process it. And this information can be something they collect in the field, but can also be something they observed in the control room and took action on. And then the third project, digital architecture for automated plant, is focused on enabling a uniform data platform for nuclear power plants. And let me explain to you why we need this project. So currently in a nuclear power plant, because they're relatively old, and there are many solutions that came in and went out, solutions for different aspects of the plant, including the business side. If you go into a nuclear power plant, you might have a dozen or even maybe 2 dozens of different tools and softwares they use for different things. So if you talk to a system engineer, who is the person usually responsible for some equipment, they use their own tools to evaluate this equipment. And then you might go to another organization and find out that they use different tools for different purposes. So we have islands of data that are, and a lot of data that are not really integrated in any way. And now when we want to introduce automation, we want to start meshing everything together and getting this broader data sets that can be used for various automation activities. And that's what this project is focused on. In addition to that, we also do some business decision making here. So we do some data analytics with regards to text, and I'm just going to show you an example today. But we also do predictions on what kind of demands the plant would have, for example, in inventory, and I'm going to also show you example today, and so on. And then the human technology and integration has also two projects. The first one is, as I mentioned earlier, focuses on coupling the human aspect with the technology and what is the optimal mix of the two. But the second one is actually more generic, and it looks at an overall roadmap for everything I just showed you. So creating a full nuclear plant modernization plan. And finally, ION is what I mentioned earlier, which is the business side of things. So now we went into multiple levels of zoom in. Now we're gonna go into the scope of what I wanted to present today. So anomaly detection and condition monitoring. So if you looked at this curve or this figure, and you start from the left, time to failure, and go all the way up to the right to the failure, you'll see on the top the different kind of stages equipment go through. So you start at normal. There's some normal wear and tear when you're aging, and then there are some accelerated wear and tear when you get closer to the damage, and then there's an abnormality and then a failure. In our industry now, we have different mechanisms, which I'm showing at the bottom, to fight against all those different stages. So on the extreme left, we have something called aging management. That's when they look at things that didn't fail, but they just kind of predict how long they have with this specific structure or component or system. And then they do the maintenance activities. There are some surveillance, some monitoring aspect there. And then operators are usually tasked looking at alarms. They might do some rounds in the plant to go around and look at the plant. What we are trying to introduce here is this anomaly detection part. And there was previously, there have been some tools that are used in monitoring and diagnostic center called advanced pattern recognition. So they basically do the same thing, but they are more primitive. And the aim here is to find those anomalies or these issues before they become alarms. So once you hit alarms, you have a very, very short lead time to prevent the failure. And as I mentioned, operators operate in this regime, in the alarms regime. And we wanted to give them a bit of a lead time for failure so that they can maybe mitigate those and avoid the failure. Most of the time, everything you see on the right side is very data driven. Everything you see on the left side is very model driven, like aging management, because you don't have a lot of data there. You are very model driven. And as you go to the right, when you get to alarm, it's just purely data driven. All right, so this is an example to clarify what is anomaly detection. So, and this is a real example. This was from a nuclear power plant we worked with. And this nuclear power plant, they just bought some fans. So, you have the drywall in the nuclear power plant, and it gets really hot because that's where the core is, dissipating here heat into the drywall, and it gets warm. So they have fans at the bottom. I'm sorry, I don't have a laser pointer, so I'm trying to use my finger as much as I can. At the bottom here, yeah, you can see that. So they have those fans, and the aim, the task or the function of those fans is to just push the air or the nitrogen inside upwards, so that they take the heat up and it gets dissipated outside the drywall, and then it comes back down into the fan. So what happened is they had 4 fans, and they are brand new fans. They were like 2 years old. One of them failed, and they don't know why. But as if they were looking into why it failed, within a couple of weeks, the second one failed. And when the second one failed, they didn't have enough cooling in that drywall, so they had to shut down. And they had to shut down for multiple days, for 6 days. And do you know how much does it cost for a plant to shut down a day? And that's a minimum estimate. I mean that's on the low end, $1 million. So it's a lot of money lost energy wise when the plant shut down. So the optimal solution was okay. why did this happen? Do we have any sensors on the fan? And they realized that they don't have any sensors on the fan because they were brand new. They didn't expect them to fail. So can we install sensors on the fan? Well, you can't, because this is a very radioactive environment. You are not going to just go in and install sensors in the middle of with the plant running. It takes a lot of work and effort to do so. So they said, okay, so what else can we do? And they said, well, can we from other sensors, can we infer the conditions of the fans from other sensors, which I'm showing in red dots here, that exist in that environment? And those red dots are mostly temperature measurements. Some of them are humidity. There's some flow measurements, and so on. But again, the vast majority were temperature. Now, if you think about it logically, if the fan is failing or is degrading, what's going to happen is that your temperatures are going to start going up. The cooling is not going to be effective. So from a logical point of view, we said, okay, we think this can be detected, but let's give it a shot and see if we can catch it. And I'm actually showing you here the picture of the actual failure that they took of the fan when they went in and looked at it. All right, so in machine learning, and I apologize if this sounds trivial to some of you, because I asked about this presentation ahead of time, about the experience of the audience, and I was told to keep it high level. So I'm gonna start with simple things that we applied. So we have clustering methods. So when we have this data from all those sensors, let's say we had, I think, 36 sensors, and now we're trying to basically group them into states. And the question is, how many states do we have for those fans? So you might come up and say, oh, well, I have two states. One is normal and one is abnormal. But in reality, that might not be the case, because you remember how I told you there are 100% power and lower power. It's the same thing here. There are different environments or conditions that would require you to have different stations, just one or two states. In this case, we applied something called clustering, which is when you try to group the data that looks similar together in groups. And we realized that the optimal number of states or clusters was 5. And then we did this. When we did this, we saw there are a lot of anomalies. So look at the red dots. Every red dot is an anomaly, and every blue dot is normal. So many red dots that this is useless, because if I give this to a nuclear power plant, I'm telling them there's almost an issue almost all the time. So this having a lot of false positives doesn't help. And this was not our, this was our initial try, but we worked on optimizing the clusters so many times, and this wasn't just a quick run where we just showed the clusters and so on. We tried to reduce the false positives as much as we can. We couldn't. This was 5 years ago. Then when we started working on this, and then we said, okay, let's do some other algorithm. There is something called isolation forest. So in this case, you can isolate every event into 2 states, normal and abnormal. But as you can see, same issue, lots and lots of false positives. So that didn't work either. So we said, let's change how we're doing this. Let's go into prediction. So instead of building classifiers, which can tell us normal or abnormal, let's do regression, and let's try to predict some values of the sensors. And then when we actually get the measurement from the plant, we can compare prediction versus actual. And if our prediction doesn't match actual, that means there's an anomaly. And when we say if my prediction doesn't match actual, then we have to add a metric like the one I'm showing you in the middle. We did an F-test in this case, and we compared some variances of some windows, and we can figure out if the departure between normal and abnormal, or what is expected and predicted, what was predicted and actually measured, is large enough that it justifies that for us to declare that this is an anomaly. This also worked fine, also had false positives, not so much though, but we ended up moving forward. I can't show you everything we've done because we actually moved on to something called autoencoders to do so, and that was also giving us better results. But the main theme of everything we did here was we still got lots of false positives, because keep in mind, this is a data-driven approach. This is not, so we're just filling the data, tell us if there's something wrong. Now, one of the interesting things we noticed here, and I'm showing this here for a reason, is look at 12, right? You see that huge bar that's saying something's wrong there. Actually, maybe I should mention this. So in this approach here, we broke this into windows, and we had 12 windows, or sorry, 14 windows. And some of the windows were very anomalous, meaning they showed a lot of huge variance in the data. And 12 is actually not an anomaly. 12 was when power changed. They had to drop power for some reason, and 12 flat. And you can see how bad the power change is compared to the anomalies, which is I think 1 or 2, I don't remember exactly. But it's orders of magnitude higher, which is why when I had the first slide and told you we're working on transients, we're trying to isolate all those false detections because they shadow everything else. Now, as I mentioned earlier, the common theme, we have a lot of false positives. And if it has a lot of false positives, we are not going to be deploying this because you don't want to keep calling the plant and saying there's something wrong and they have to go in and investigate. So we saw this as a big hurdle. So we said, okay, we've tried with unsupervised methods. We can't get them to perform perfectly. And by the way, you might ask, why don't we just develop models for everything? We can develop models for specific equipment that are important, like the fans, for example. Maybe we can build a model for that. But can you imagine how many equipment like those we have in the plant and how many models we have to develop? Lots of modeling. So I always mention that there's no one solution fits all. If you're focused on a certain equipment and you think there's value in investing in the development of a model, you should do it. But if you are applying something that applies to everything in the plant, and that's what we're doing here, and typically the plants would have thousands of sensors, you would want to probably go with a data-driven approach. So anyway, lots of false positives. So what do? We said, okay, we know that there are some failures that happen. And I'm showing you here examples. Might be your data set. Well, you have some sensors, and you know that at certain points of time, you had some issues. Just like, let's look at the fans. Those red regions might be your fans failing. So we know that there are issues there. Now, can we use that insight from those failures to improve our detection? And because of the fact that we don't have labels for everything we have labels for certain regions, that's called semi-supervised. If we had labels for everything, that would be fully supervised. So we actually looked into that. And one of the things we had to do, actually, I have to speed up a bit. So we had to build a simulator. So we don't have labels in the plant. We work very closely with the industry. We have data from the plant, but we don't have a lot of anomaly labels in the plant. So we built this 3-mass system simulator, and this is just a mechanical system that you can see with springs and forces and so on. And then this simulator has some features. You can make it linear or nonlinear. You can actually scale it up and add more masses. We went sometimes to 10 masses, and it's all high-order differential equations. And the reason we did this is that this actually resembles to some extent what you see in the plant. You have multiple systems that are coupled to certain extents. And if we change the spring damping coefficients or the dampers coefficients, we can get the coupling to be stronger or weaker. We can manipulate that. And then we start adding anomalies to this system. And there are different types of anomalies we can add. So we can add anomalies to the spring, or the damper. We can also have different shapes, so we can have something like ramp or step, and we can also control the magnitudes for the anomalies. So we wanted, whatever we want to create, we wanted to test it before we actually apply it on real data. And this was our tool to do so. And as you can see, if you look at the left, this is your raw data from the spring mass system. And there's no way on earth you can tell where the anomalies are, because if you can't tell where the anomalies are, you shouldn't be here. You should be working for the CIA or something. So that is really hard to detect. But actually, we're showing you here a zoom in, and you can actually see that there are some. Well, actually, you won't see, but there's a dashed line that tells you that this is an anomaly. Again, there's no way for a human to do that. The machine can't distinguish those. But this is the data we get actually from. I'm going to speed up more because I'm realizing we're almost out of time. So for the semi-supervised case, we had 2 different approaches that we looked at. So remember, we told you we have some labels, right? So if you look at that shape to the left here, there are some black dots and some white dots. And this is if you look at your data in 2 dimensions. Let's say you have a way to convert this data from multi-dimension to 2 dimensions. You'll see something like this. Now, what you want to do is you want to separate the normal data from the abnormal data and create that kind of boundary to say that everything within this boundary is normal, everything outside is abnormal. And there are methods out there to do so. One of which is called DeepSat. DeepSat, what it does is actually converts your multidimensional data into kind of a sphere, and it compresses all your normal data into a cluster, and then spreads out all your abnormal data. So as we get more and more labels, the sphere gets adjusted to kind of keep compressing the data and pushing everything out. And then we created our own approach, which I'm showing down here. And this was a bit different, and this was actually done in collaboration with Purdue University. And you know how when you're trying to fit a line to let's say a linear regression model, you have parameters and coefficients that represent the contribution of every variable. What we did here is we looked at the different, we use the labels we have or some of the anomalies we have to decide which out of those coefficients is important to anomaly detection, and then pick them up. And I'm showing you here an example where we picked one of the features that can show you very clearly, compared to the one to the left, that there are anomalies happening in those red regions. So you can actually figure out what kind of features you need to extract specifically from your data that can highlight the anomalies you're looking for. And we use the labels we have for the sparse anomalies to do so. Here I'm showing you some results from both. So the one to the left is using DeepSat. And what you see here is a blue line, which is your anomaly score. And then you have regions in blue that basically tells you that there's an anomaly there, but we haven't labeled it. So the first one has no labels at all. The second one has 2 labels at the beginning, and all the other anomalies are not labeled. And as you can see, as we're adding more labels to DeepSat, it's starting to recognize more the anomalies. It didn't work perfectly, and there is a reason why it didn't work perfectly. But you can see that peaks are starting to show up as you add more and more labels. I'm showing you also the other one, the high order feature approach, where we added 1 label at the beginning, and you can see almost immediately a lot of the peaks have shown up. So this shows very, very promising. And that was one of the reasons why we looked at this, because this wasn't working very well. Not because DeepSat doesn't work very well, because I think we were learning the process, and there's a lot of hyperparameters tuning we have to do to make it run the way we want to. But anyway, so we tried both approaches, and the aim here was to validate that with semi-supervised machine learning, we can get better performance than unsupervised. And this research achieved that conclusion, and that's what that is why we did this in the first place. All right. So the question is, I just told you everything about semi-supervised and how we have that three-mass system, and we can add labels because we know where the anomalies are. We can force anomalies and label them. But in reality, in a nuclear power plant, do we have labels of anomalies? Remember, I told you we don't. We don't know where the anomalies happen. So why did we do this whole research if we don't have labels? Well, because we have ways to create those labels. So this is actually a technology that we created recently, and it won an R&D 100 award this year. And everything that happens in your plant, 10 minutes. Everything that happens in the plant gets logged in a condition report. So if you are working in the plant and you see anything wrong, you are supposed to go and log it in the system. Say, I was walking around and I saw this broken, or that's broken, or there's a safety concern here, or whatever. And there are people that review those and make decisions on what needs to be done. So what we did is we created an algorithm, or a machine learning algorithm I should say, instead of an algorithm, a set of tools that would automate all these decision-making processes. And I'm showing here 4 example decisions being made. So one of the questions being asked is this event safety related? Because it has a different weight. It would be treated very differently if it is safety related than if not. What kind of priority should we give it? Who should be working on it? And I was mentioning today earlier that you can actually have more than 100, almost 200 decisions. I've seen 200 decisions being made on one condition report. So you have a lot of decisions being made by people. And we wanted to automate these processes. But one of the key aspects of this is the keywords box. If we can automate the keywords assigned to every condition, that enables us to do trending. But let me explain to you what I mean with keywords. Currently, whenever there's an event, people in the plant have to classify it. They have to decide, all right, is this related to valves? Is this related to HEMA performance? Is this related So what do we classify? Is it housekeeping? So they have to label this event with some labels. The problem with that is this process is very subjective, and not everyone does it. I mean, sometimes they go with the other box because it's easy. So you end up with a very messed up labels. And if you want to track how many events you're getting in one facility over time, you're not going to get accurate results. So we automated that process too. And I'm not going to give you a lot of details on how we did it because that's outside the scope of this presentation. But if I have text like the one I'm showing you here, the top, sorry, you can read it. It will assign those words to it, and those are actually assigned by the machine. And I'm showing you even the weight for everyone. So how confident was it in those assignments? And if you can look at those assignments, it's very context driven. So we created a way to label those events as they appear in the plant with a set of themes or topics that are relevant to that condition. Now, why do we do that? Because once I have that, I can create trends like this. So I can count how many times, for example, if I'm looking for communication equipment, which is there, I can count how many times did we observe this every month, and then create a trend like the one I'm showing you here. And also the other reason why we can do this is because this we can also feed into anomalies. So we can actually catch anomalies in the text. We can now generate those labels I told you it's missing. So now we have labels that we can use with the anomaly detection algorithms we have to improve their performance. Those labels were not there before. So this was a different research, but there was a kind of a coupling between this research and what we just showed you. And this is the source for our labels. All right, last topic for today's presentation is root cause analysis. So given the time, that fact I'm almost out of time, I'm gonna rush even further. So there are two different ways when you have an anomaly and you want to do root cause analysis. Currently, most of the researchers, when they look at this problem, they say, let's build a model of the system, because if you build a model, you can basically simulate all the different causes. You have patterns of data that you can compare to what you're seeing, and you can determine the cause of the anomaly. But remember, we're doing unsupervised. We don't have models, and we don't have any knowledge about previous anomalies. So there are two different hypotheses we tested in this research. The first one is called contribution-based, and the idea here is that, or the hypothesis here is that if you have an anomaly in the plant, the cause of the anomaly is usually the highest contributor to the anomaly. So if you have a set of sensors, and I'm going to show you an example, most likely the sensor that's going to show the highest anomalous behavior is going to be kind of around the cause of that anomaly. That's the contribution-based. The time-based is a bit different. The assumption here is that if you have an anomaly and you look at your different sensors, the sensors that initially show the precursors to the anomaly are usually associated with the cause. So you assume the anomaly propagates in time. That's the second one. The first one, you assume the anomaly propagates in space. And these are the two hypotheses. And we've looked at different methods, and I was planning to talk about them more, but because I'm running short of time, so I'm just going to skip them. But the idea here is there are different ways you can validate or figure out what the contributions of every sensor is. Same thing for the time. And we evaluated this with the system I just showed you. So for example, we created an anomaly on P01, which is the spring mass in between mass 0 and mass 1. And look at this. This is what all the sensors we're measuring and the forces contribution is. And you see blue and orange, and then maybe a bit of red are dominant in terms of contribution. And if you look at blue, orange, and red, that's S0, F0, and F1, which is right in between, basically saying it's somewhere over there that the anomaly is coming from. And this relates also to some aspect of a common topic that we talk about a lot in AI, which is transparency. Because when you see an anomaly, you want to know where the anomaly is coming from and why. And this is telling you where it's coming from. And this is another example where we force the anomaly, instead of being a process anomaly, we said, let's drift that sensor, S0. Let's cause a drift in it, because that's a common problem. They have nuclear power plants. And you can see S0 basically dominated the whole behavior in terms of contribution. So it was very clear that S0 is the cause of the anomaly. And then because we have the simulated system, we can run 1,000 anomalies, simulated anomalies, and figure out how are we doing in terms of catching all the different cases. And that's what I'm showing you here. So we ran all the different types of anomalies 1,000 times. And what the interesting thing is that when we looked at the patterns of data that we got here, we could see that there's a lot of consistency in terms of how the patterns of the anomalies are looking like. And to clarify more, we did a confusion matrix, and what the confusion matrix does is shows you, well, what is your predicted anomaly source and what is the actual one, and how do they compare to each other. And as you can see, it was mostly diagonal, which means most of the time the prediction was matching the actual. And this validated our assumption that the causes of the anomalies are usually the biggest contributor in this specific use case. Now, I'm showing you all simulated system here. We actually ran almost everything I just showed you on actual data from nuclear power plants, but I can't show you that. So I'm just showing you the simulation side of things. But I can tell you we had some also promising performance with actual data from nuclear power plants. So we also did the time-based approach. So granular causality is the approach we used. And the way we did this is granular causality creates a kind of a correlation between each variable that you have. So if we have S0, S1, S2, which is the sensors and the forces both in the X and Y axis. What this is telling you is that one sensor can be strongly associated with another sensor, meaning when something happens in one, the other one is most likely to have to show an effect from the first one. And what we did here is we convert the correlation between the sensors during normal and abnormal, because if we think about it, if the source of the anomaly usually, or the sensors that are associated with anomaly, they tend to break the relationship between their causality in the normal state from the abnormal state, or to the abnormal state. So if we compare how the sensors correlate to each other in normal state, and then we do the same with abnormal state, we create something like this. And what this is telling you here, this was on P1G, so mass 1 and ground. What this is telling you there, that the anomaly cause is somewhere around 0 and 1. And as you can see, that's where the highest difference. So this is again telling you that the correlation between the sensors, causality effects changed at these locations, and highlighting where the cause is. Also did the same thing with the confusion matrix, like I just mentioned for the previous case, but this wasn't very promising. As you can see, you ideally want everything to be on the radial or diagonal, sorry, of the matrix, and you have a lot of values all over. So it didn't go very well with the time-based, but the contribution-based was very promising. So just one last thing. Wanted to show you some examples of other things we're doing. So most of our nuclear power plants have analog gauges like the one I'm showing you to the left. And what we're doing is we are creating machine learning methods to read those gauges automatically. So someone can take a picture like this guy, and all those gauges in the panels would be read automatically. The reason I mentioned this specifically because most of what I'm showing you here is the image-driven analysis. Everything I just presented to you today was time series and sensors values. And then I gave you a bit of insight about natural language processing. We did some work there. We're also doing work on image processing, reading gauges, fire detection. I'm showing here 6 different models that are running. And if you can, I don't know if you can see this, but there's a small text that goes red and blue, flame, no flame, with the confidence as cars or smoke covers the fire. So we built a model that I think we are now at 99.7% accuracy. And then should play this. So we're also using enabling drones to fly in nuclear power plants. So there's a small box there, and there's a small drone. I don't think you can see it. It's very tiny. It's moving in a bath, and we're trying to enable drones to look at visual features in environments, to enable them to navigate those environments to replace people. We're also working on predicting. One of the challenges in nuclear power plants is they have a lot of stocking requirements. So they adopt a conservative approach when they're stocking parts for the plant. And this results in more than $100 million typically in a nuclear power plant of inventory. So we're trying to couple those stocking requirements with the work demand in the plant to better predict what you need to reduce the minimum stocking requirements they have. So lots of cool stuff that's going on. And we're always looking for interns. So I'm gonna mention there's my email. So if you guys are interested in coming to INL and working for us, at least interning for us initially, you can always apply online, inl.gov, or send me an email and I can forward it to the person in charge. Thank you so much. And I hope I didn't bore you with this. I know I talked too fast.